Okay, good morning. Another session, logic design. We're almost there. Three or more, three or less. I think we'll be done with the whole course 112. The last time we talked, we introduced the D flip-flop, and we called it the data flip-flop, a memory element used to store data. Last time we introduced the D flip-flop. Right, what is the D flip-flop? The D flip-flop is basically a modified form of the SR flip-flop. Modified how? There is an inverter which is added between the S and R inputs, and both are joined to form only one input known as the D input. So from our SR flip-flop, we had something like this: 4 nines, S and R. Then we have the clock. This. Output Q, output Q bar. All right. This is our SR flip-flop. We know its behavior from its truth table. I think I put too much emphasis on that truth table. The behavior of the SR flip-flop, you know it from the truth table. You can deduce the characteristics table. You can go on and find the excitation table. We all know the characteristics, how the SR flip-flop behaves. The D flip-flop is just a modified version of the SR flip-flop. How S and R, they are joined. So I can do this. S and R, they are joined. So we no longer have two inputs here. We only have one. This is removed. We have D. There is also an inverter added between the S and R. An inverter added between the S and R. Here we have an inverter. Voila. So this becomes my D flip-flop. Almost the same as the SR. Only difference is one input, S and R are joined. There is an inverter between the two. What of the characteristics? What of how does it function? It removes, I think best way to explain it. Let's start with the truth table of the SR. Truth table SR. SR. Truth table, we have S, R, we have Q plus. Zero, zero, 1, 0, 1, 0, 0, 1, 1. I don't need people in the chat, please. I do not need people in the chat, right? My Q next, we know that this is the memory state. This is the reset state. This is the set state. This state doesn't exist, right? From the truth table, from this truth table, we can see that if we want to store a 0, this is how we store a 0. If I want to store a 0, then my inputs, S and R, they become 0 and 1 respectively. If I want to store a 0, S is equals to 0, R is equals to 1. If I want to store a 1 using an SR flip-flop, what do? My S becomes a 1 and my R becomes a 0. We can note that if I want to store a 0 and if I want to store a 1, the inputs S and R, they are complemented. Complemented in the sense 0 changes to 1, 0 changes to 1, and vice versa. This means instead of having two inputs S and R, why not have one input D and put an inverter on it? Put an inverter on it. Now, if I have 1 here, it means the other input is 0. If I have 1, the other input is 0. Now it means I'm storing a 1. If I have 0 here, the other input is 1. Then it means I'm storing a 0. So the modified part, why modify? Because we want to keep only these two. Store a 0 and store a 1. Complement of the S and R simplifies to having only one input and we complement it. That's why we have the D flip-flop used to store data. So what you do, if you want to store data, we have the diagram here. If you want to store data, what you just do is give the input D. When you give the input D, you remove the clock. Now you've stored your data. No, but didn't remove the clock. If I remove the clock here, then whatever the input was, if the input was 1 here, then it means I have my Q next is equals to 1. It is stored. If I remove the clock, Q remains as 1, storing data. If I input a 0, the output Q is equals to 0 is stored. All right, to the truth table. To the truth table of the D flip-flop truth table, I have the clock, I have the D, I have the Q next. If clock is equals to 0, what happens? If clock is equals to 0, whatever the input, we have the memory state. So here we have Q. This is the memory state. I probably didn't explain this last time. What happens if my clock is 0? If clock is 0, it means here we have 0, here we have 0. This is a NAND. This is a NAND. 0 times everything. Here it means output will be 1. At this stage. At this stage, the output will be 1. For a NAND SR flip-flop, we have it being an active low. So when we have a 1, 1 here, it means this is the memory state. Probably something I didn't explain last time. Let me do this. If I have an SR, a large with NORs. This is active high. Active high. So it is something like this. A NOR. This will be helpful explaining most things going forward. So we have a NOR gate. We have a NOR gate. We have output Q. Output Q bar S R. Right. This is NOR's active high. This is NAN's active low. 4 NANs. 1, 2, 3. Well, let me start by doing this. Only 2 NANs. Watch. Only 2 NANs. We have Q bar, and this is where the active low and active high comes from. S bar, R bar. All right. There's a huge difference between these two. The inputs here, they're high. The inputs here, they are low. R bar, here we have R, here we have R bar. That's where the active low, active high comes from. So what this means, if I have for input high, if I have a 1, S is equals to 1, and then R is equals to 0. This means this is my set state. Then for the inputs active low, I will need my R bar is equals to 1 and my S bar is equals to 0. This will mean set state. The inputs here are 1, here 0. The input here 0, here 1. The result is the same. Set state, set state. But the inputs, they are not the same. Because of this, NOR and NAND. The NAND one can then be modified because we know what S bar is. S bar, how do we find S bar from S? If I have S, then here I have S bar. So it means I can do this. Put another NAND. Now I have an active S. Put another NAND. Now I have an active R. That's why sometimes I put it up as 4 NANDs instead of 2. Now my inputs are high. But when I go to the output, they are low with the bars. The truth tables for these two, they are the same. But how they behave, it can be different here. Active low and active high. So going back where I was here, I was explaining what happens when the clock is 0. And I said when the clock is 0, what do I have? For this NAND, NAND 1 and NAND 2, if the input is 0 for a NAND, then the output automatically is a 1. Now, if I have a 1, 1 for these NANDs, this is what we call the memory state. If I had NORs here, then 0, 0 will mean the memory state. But here in this case, I have nuns, which means a 1, 1 is the memory state. That's why I have the memory state when clock is equals to 0. It explains for all the flip-flops we've done and we are going to be doing. When the clock is 0, we are in the memory state. When the clock is 1, D is equals to 0. Q next is equals to 0. This is the reset state. D is equals to 1. Q next is equals to 1. We have the set state. So the D flip-flop is much easier. The truth table, very small. Now, the characteristics table. Characteristics. It shows you what the outputs, the next outputs will be provided the present state. So for this one, what we have the input, the present state Q, the input D, and the next state Q plus 0, 1, 0, 1, 0, 0, 1, 1. So if D is 0, what will be my Q next? How many participants we have? 24. Anyone with a very good network to respond to that. Refer to the truth table.
It's a 0.
It's a 0. Why? Why is it a 0?
It's the reset.
Reset state. And for this one, it's a 1.
It's a 1.
The set
state.
And for this one, this goes to 0,
0,
1, reset, set. This is how we come up with the truth table. Do the same. You can find the excitation table, which is Q plus D. What do we need to do? What do we need to do? So if I want to move from the present state 0 to another state 0, what do I need to do? I need to input my D as 0. Here, 1, 0, 1. Very simple stuff. We have one acknowledging this is true. So it means the rest of you probably understand. All right, this is the data flip-flop, the D flip-flop, and we are done with it. We move on to the JK. All right, the JK flip-flop is also a modified RS flip-flop. Another RS flip-flop modified. Why? To remove what we call the race condition. For the RS flip-flop, when RS goes to S, is goes to 1, what happens? Participation. For the RS flip-flop, when RS goes to S, is goes to 1, what happens? Where is the RS flip-flop? There. What happens when S and RI goes to 1 for the RS flip-flop?
It's illegal.
It's illegal. Why is it illegal? We have what we call the rest condition. That illegality is what we call the rest condition. Now, what the JK flip-flop does is it eliminates the rest condition. We now have a case where we can have R and S being equal to 1 for the JK, but they are no longer called R and S, they are now called J and K. This is no longer illegal. It is replaced by the toggle effect. Replaced by the toggle effect. Now when J is equals to K is equals to 1, if my Q is equals to 0, my Q next will be equal to 1. It toggles, it flips. If my Q is equals to 0, if my Q is equals to 1, my Q next will be equal to 0. So what the JK flip-flop is, it is a modified RS flip-flop with feedback which eliminates the race condition, the illegal condition we had. Now it eliminates and replaces that with the toggle. Is it called the toggle effect? I don't know where I got the toggle effect from. Let's say it's the toggle effect. I know toggle is there. I'm not sure about the effect. It replaces it with the toggle effect. What happens with the toggle effect? Now when J and K are equal to 1, we have the outputs flipping. The next state is always opposite the complement of the present state. So briefly, this is what the JK flip-flop is. All right. So what we have, the modification, it happens like this. We have 4 nines. The first output. All right. So this is output Q. We have our NAND. This output Q bar, Q complement. Then we have our clock. This is our clock. Then we have our J. We have our K. For the RS flip-flop, the RS flip-flop is like this. We begin here, S and R, with our outputs here like this. This is RS flip-flop. Now we have feedback. We modify it by giving this feedback. Q plus goes back here, and Q goes back here. And now the S and R, they are no longer S and R, they are J and K. And voila, we have the JK flip-flop. With this feedback, we have eliminated the race condition and we have replaced it with the toggle effect. All right, the truth table. Let's start with the truth table. It is almost the same as the RS flip-flop. But the difference is we no longer have a legal state. So 0, 1, 0, 1, 0, 0, 1, 1. Here, this is the memory state. Same as the RS flip-flop. This becomes the reset state. Reset. Same as the RS. This is the set state. Same as the RS. Here, we have the toggle state. We no longer have that illegality. We have the toggle state. What this means is, if my input was Q, then my next state will be, if my present state was Q, my next state will be Q bar. 0, 1, 1, 0. That is the toggle state. How does it come to happen? That is for you. Both of you is a lot. How many minutes do we have? How does it come to happen? That is for you to do a little bit of research. But we can continue with the truth tables. I'm no longer going into this and deriving the truth table. I'm no longer going to do that. You all know the knowledge, you all have the knowledge of how a NAND operates. So you can do the math. What happens if my J is equals to 1 and if my K is equals to 0? Do the math. What is my output here? What would be my output here? You will get the truth table, believe me. I did that for the SR flip-flop. I choose not to do it for the JK flip-flop. Right, this is my truth table. Same logic applies when I want to find the characteristic table. Same logic as before. I need to find the characteristics table. So now we have, what is the characteristics table? It shows us what the next state will be. So we have our current state Q, our inputs J and K, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. Right, participation. What will be my next state? Same logic as usual. If my current state is 0 and my inputs J and K are equal to 0, what will be my next state?
0.
0. Next one.
0.
The next one, 0. Next one.
1.
1.
1.
1.
1.
Nope. Yes, this is 1.
1.
What happened here? This is toggle. I'm more concerned with this one.
Q bar.
Exactly. We have 0. Then here it's Q bar. This one is the set. This one is the reset. Right, we continue. Here we have 1. Next. This is 1. What happens to 101? So this is 1001. 101
to 0.
to 0. Reset. Here we have
That's a 1.
1. And here
That one is a 0.
is 0.
It's a 0.
Thank you very much. It means we are going somewhere. It means we are going somewhere. This is the characteristics table. From the characteristics table, I can add what I call the characteristic equation. What is the characteristic equation? It shows me what my Q next will be. If I use the K-map, I can use the K-map. If you use the K-map and you have 8 variables here, for each variable, you have the outputs 1, and you use sum of products, believe me, you find Q plus being equal to J Q bar plus this. I'm not going to take you through the K-map. We all know what the K-map is. If you minimize what the output Q plus is, you will get this using the K-map. I've introduced the characteristic equation. Now, I can go on to find the, let me remove this, and we put the excitation table of the JK. The excitation table, it shows me what I need to do to change states. What do I need to do to change from one state to another? So if I want to change from state Q to state Q plus, what do I need to do with my inputs J and K? Right. If I want to change from 0 to 0, here I'm changing from 0 to 0. What happens? Anyone who's ahead of my time, please tell me what happens to J and K.
It's a 0, 0.
0, 0 here, but there is another one here, which is 0, 1. So for these two, they both allow me to change to remain in the present state, 0, 0. So we have J is equals to 0 here. But K can either be 0 or 1. It means we don't care what K is. Right. If I want to change from 0 to 1, here I've changed from 0 to 1. Here I've changed from 0 to 1. So we have these two here. In the red, J is equals to 1. We don't care what K is. Do we agree? Someone understanding what I'm
Yes.
saying there? Thank you very much. Right. If I want to move from 1 to 0, here I'm moving from 1 to 0. Here I'm moving from 1 to 0. What is happening here? We have this. We have this. My K is equals to 1. I don't care what J is. Put that in another color. I don't care what my K is. I'm moving from 1 to 0. This is 1 to 0. This is 1 to 0. 1, and I don't care. Right, if I want to move 1 to 1, 1 to 1, I have this in yellow, 1 to 1. I also have this, right? My K is equals to 0. My J, I don't care. And voila, we have the excitation table. And this is it with the JK flip-flop. I think one important feature, which also leads to its name being called the toggle, the flip-flop with the toggle. One interesting feature of this is the toggle, the changing from 0 to 1, 1 to 0. Otherwise, everything else, it performs the same as the RS flip-flop. I think we can see most of the flip-flops that we are adding, they all originate from the RS flip-flop. The limitations of the RS flip-flop, they lead us to some of these, the JK and the D flip-flop. 1 minute 58 seconds. Any questions? Any comments? Right. There's a chat. Say I'm hardly hearing you. Anyone who can hear me clearly? The network is bad.
Say.
Yes.
Say.
Yes.
If you tapeza lesson, can you explain what teach about truth table when about characteristics table? How we are having a hard time to understand that.
Right. I have 1 minute 22 seconds to do that. Very simple. Okay, let me respond to that in the next session. Let me respond that in the next session. We are out of time. Join me 5 minutes. I need 5 minutes to reset. Join me after 5 minutes. 11:45.